Okay, if no, let me actually go over one more topic, which is how do you assemble a matrix element by element. This is important because we ultimately want to generalize the finite element method into 2 and 3 dimensions. And actually in the project, you are going to be seeing a finite element in 2 dimensions. Okay, so in 2 dimensions and 3 dimensions, it's very important to figure out how do you assemble the matrix, which is going to be more complicated than in 1 dimensions. But the idea, once you know how to assemble a matrix element by element, the method actually generalizes very naturally, almost without modification, to 2 and 3 dimensions. The idea is that our matrix Aij is the integral from 0 to 1 over the whole domain of the product of 2 derivatives. All right. And this integral can always be decomposed into a summation. Let's say k goes from 0 to n minus 1. This is a summation over every element, okay, in the domain. And the integral, of course, is split into xk to xk plus 1. So this is integration over a single element. Okay, so essentially the big matrix is split into the summation of equally big matrix, but each matrix is just the integral of the product of a pair of basis functions on one element. And the reason why this is helpful is because such matrix actually is extremely sparse. Exactly how sparse is it? By sparse, I mean there are only very few entries in the matrix is non-zero. So exactly how sparse is this? Let's just look, right? Let's just focus one element. So this is xk, this is xk plus 1, x and the fees. Can somebody tell me which pairs of I and j, when you multiply their respective derivatives, would be non-zero when integrated over this element? Okay.
Is it just xk and xk plus 1?
Yes, actually, that's exactly right. So only when I equal to k or k plus 1, and when j equal to k or k plus 1, there is any hope of this product being non-zero over this domain, right? Because phi of k is this head function, of k plus 1 is this head function, right? All the other basis functions are something like this. I mean, they are completely zero within the domain we are considering. So essentially, if you look at the whole matrix, how many elements are non-zero? Can you count how many elements would be non-zero? How many combinations of I and j would make this we call element matrix non-zero?
4.
4, yes. 2 i's, 2 j's. So would be 4 elements like this. So this is the ith row, the jth row, this is the ith column, jth column. Only these 4 are non-zero. Okay? And the code for computing, if you program what is required for computing such integral, it's actually the same for actually any k. So let's actually go back to our MATLAB and figure out what that is. All right, so let's go back to our computation of A and modify that to make it a bit more general. So instead of looping over the diagonals and computing the diagonals, and then looping over the off diagonals and compute off diagonals. And you have to treat the special case where, okay, my basis function is at the boundary, and this is not at the boundary. This is not at the boundary, and this is at the boundary. I'm actually going to get rid of all of them. So I'm going to